always do that. Somebody's got to just like check on me
You
every
had
day.
it up.
I know, but I paused it and I didn't. Somebody's got, whose job is that to just check every day?
Oh, I can definitely.
Okay, there you go. So that's your job. Check and ask me if I'm recording.
Oh, I can.
Is that what you wanted?
Yeah.
Okay.
She was here and then she left.
Okay, so let's have a look at this function now. I'm going to show you where it is on the calculator too. Okay, where is this guy? So if you go y equals greatest integer function, I have to remember this. I think it's under math, and it's probably going to be under numbers. And it's right there. It's number 5.
Math number 5?
Yep, math 5. So that's the greatest integer function. We'll just put an x in there. Oops, I can't do that. Hang on. I got to use the x, close parentheses, and let's just hit zoom 6, and that's going to look, I'm going to maybe make it a little smaller. Okay, there it is. Okay, let's focus in a little more closely. I'm going to go to the window, and let's just go from -4 to +4. Oh, what'd I do? Oh, it's got to be negative. Whoops. -4 to +4. Zoom fit. I put a minus sign instead of a negative sign.
Are you sure it's number?
There you go. Okay.
So what do you put in? Those don't look like
They are. They are. Okay, so does everybody see this? Does everybody get this to work?
Yes.
Okay, what this is a stair-step function or a greatest integer function. So it's int. It's in the math menu. Math number, I think it was 5, right?
Yes.
Math number 5. Okay, the definition of this then, doesn't this make sense? This is giving us back for the input of any real number, it's going to spit out the greatest integer that is less than or equal to that number, right? So if I input something like 3.3, what's it going to give me back? 3, right? If I input 3.9999999, what's it going to give me back?
3.9.
No, it's going to be back 3,
Oh, yeah.
right? The greatest integer that's less than or equal to the input, right? What if I put in 4? 4, okay. What about 4.000001?
4.
Okay. What about negative 0.573?
0.
No. Negative 1.
Oh, 5.
Oh, that, you know that.
Because it's the greatest integer that's less than or equal to. What about negative 2.3?
Negative 3.
Negative 3.
3.
Right. Here's maybe a good mental model for quickly being able to work with the greatest integer function. And maybe this is overkill, but I'll give it to you real quick. Think about beads imagine that you've got beads on a string, and at every integer on this infinite string, it's like the number line, at every integer there's a knot that prevents the bead from sliding. So whenever you attach a bead to the string, you're just going to push it to the left as far as it'll go, right?
Yeah. Oh, that makes sense.
And then it's going to stop at the next integer, right? Okay, so make sense?
Yeah.
Okay, so if we can test this, like if we do trace 2.3, sure enough, it gives us back a value of 2, like it should, right? What if we go trace?
Wait, I thought you said that it was 3.
No, 2.3 would be 2, right? Because it's going to be the greatest integer that's less than or equal to 2.3. Oh, did I say? Well, did I say 3.3? Look, I put in 2.3.
Maybe did you mean negative?
You said 2.
No, I did.
Negative 2.3 was negative 3.
Well, negative would, yeah. Yeah, negative. This is positive.
Yeah.
Okay, let's try negative. If I trace
Wait, why is it doing
negative 2.3. Oh, it's going to do that again. I have to use the negative sign.
What did you actually
The minus sign.
When I use the keyboard on my computer, it does that. Okay. Negative 3, right? Like it should. If I put in an integer, it works properly also. If I say trace 2. Yeah.
So there's multiple y's for different.
No, there aren't,
Or
though.
there's multiple x's for one y.
No, there aren't. It looks like they overlap, but if we draw this more carefully, and this is where the calculator, okay, this is kind of what I'm talking about. There's just a little too much. So, okay, so if I draw this, the calculator's deficiency is it can't draw open and closed circles. That's what it really should look like, isn't it?
Yeah.
Right? Because when I get to, would you agree, when an ant walks along this function from left to right, as soon as he gets to another integer, he jumps up to the next stair. Okay. So it really doesn't overlap. There's only one, it's only defined for one y value for every x value. It is a function.
But then how come you're getting polar?
Well, that's okay. That's okay. That's because that's the mapping that exists here. It's telling us that the only output values are they're discrete. That's okay. That's okay. This is right there. You can never get an output value of y equals 2.3. It's just never going to happen because the greatest integer function only gives you back the greatest integer that's less than or equal to the input, right? So when I put in an x value of 2.3, it maps me to y equals 2.
And if you put in 2.4, then it's.
Same thing. That's okay though. That's a different x value. I can have the same y value.
That's what I meant.
Yeah, that's fine. I can have the same y value without a problem. Okay. Make sense?
Yeah.
Okay. So then, real quick, give me the answers to these.
2.
Okay. Everybody agree? The limit of the absolute value of x as x approaches 2 from the right,
Would it be
think 2.0001 or something, right? Is going to be 2, right? Because I'm putting in a number slightly bigger than 2, so the greatest integer that's less than or equal to that is 2. Okay, now by the same token, let's try this guy. So if I take the limit of the greatest integer of x, as x approaches 2 minus, what's that like?
1.
It's like 1.999 something, right? So it's going to give me back 1. Yeah, I'm approaching from the left.
Wait, why? Because can you show that like on the graph?
Yeah.
Okay.
So as we're approaching, here's 2, right?
Okay.
As we're approaching 2 from the plus direction, from the right, the ant is walking along this step. He anticipates stepping there,
And he does.
right? Doesn't matter if he does or not though, right?
Oh.
That makes no difference as far as the limit's concerned. Now, when we're approaching 2 from the negative direction, from the left, the ant is walking along this step and he anticipates stepping there, right? He doesn't, but once again, that's irrelevant. It doesn't matter what actually happens because these are limits.
Then why is it a 1 if it doesn't matter?
Because look at the y value. His y value is 1 there,
But he's coming from the one, so that's the closest
right?
lower.
Yes, right.
So
Does that make sense?
Yeah, like the plus and minus signs are like where they're coming from, not where they're going.
Where they're coming from.
Okay.
Right. Good clarification. Right. And if you think about it, that makes sense because we're approaching a finite value. So we already know where we're going.
Yeah.
Yeah. Okay.
So pretty much, okay.
Yeah, so one thing that might be helpful is for me to remind you that the output of a limit is always a x or y value. Y value, right. See, this is the x value we're approaching. This is the y value we're approaching. Okay? Make sense? Okay, so then what about this? What's the limit of the absolute value, or not absolute value, of the greatest integer function of x as x approaches -2 from the left?
Negative.
-3. And we can see that, can't we? Here's -2, and the ant's walking from the left, and his y value is clearly -3, right? Okay. As the ant approaches x equals -2 from the right, however, he would anticipate being at
-2.
-2. Yeah. Okay, make sense?
So do you always start on a different line?
What do you mean by that?
For the negatives?
For this,
For the left?
yeah, for the left and the right, you mean? On a step function, you do.
Okay.
Yeah.
For the left, you start one lower.
Yes, well, not necessarily one lower. For the left, like if I'm approaching -2 from the left, it just means that I'm somewhere to the left of -2. I don't have to start from there. I could start from right there if I like.
Oh, okay.
Okay, make sense?
Yes.
Yes. Yeah. Okay, questions on that? Yes, right.
Can you explain the -3 one real quick? Can you just show it on the graph?
Yeah, you bet. Okay, so attention up here, please. So the question is, how to get the -3? As x approaches -2 from, so x approaches -2 from the left, means I'm coming from that direction, right? So I'm approaching this value right here, that x value, from this side. So where's he walking? Well, he's walking on that function right there. And so he anticipates
Oh.
stepping right there,
Okay.
right?
Yeah.
Does that make sense?
Yeah.
Okay. Now, you can also think about this in terms of direct evaluation also, right? I mean, this is a little bit hokey, and so I don't want you to take this literally. This is not good mathematics, but it's effective mathematics. If we want to ever evaluate, or we want to determine what a limit is, and we have a function like this where we're getting discrete outputs. By the way, these are important functions. There's a lot of things in life that have discrete outputs like this. Like in physics, quantum mechanics is built on the principle of discrete outputs that exist, and there no other values exist, right? Energy functions, things like that. In electronics, TTL electronics, digital electronics, it exists based on they're either going to have a voltage that says 1 or a voltage that says 0. And so you get these discrete voltages that are being read with nothing in between. It's a square wave. And so these are really useful, extremely useful mathematical models for us to use. Whenever you're dealing with these, you can just kind of trick it and say, okay, well, what is 2 minus really, or right here, what is -2 minus really like? Well, that's like -2 point something small, right? And so if I were just to directly evaluate the function, like in my calculator, or even in my head, I can think about it that way. You guys were able to accurately tell me when I said, this is how the function works. If I input these numbers, you told me the right answers, right?
Yeah.
So approaching from -2 minus from the left would be just like plugging in a number like -2.0001 or something, right? Make sense? Okay. Does that help, Riley?
Yeah.
Okay. Other questions? Okay. All right. So now we've got what we need, right? Now we can take one more step and we can revise our definition of a limit, first of all. And we're going to use that to come up with the definition of continuity on a closed interval. We can now account for the endpoints. Remember in the past, when we've talked about a limit, we've always talked about the ant having to agree on the value that he's approaching from the left or the right. Well, maybe now we can abandon our ant definition and we can write that in terms of one-sided limits, right? Doesn't this make sense? The existence of a limit, let f be a function, let c and l be real numbers. The limit of f of x as x approaches c, right? Which we always just write, we write that this way. The limit of f of x as x approaches c equals L if and only if these two conditions are met, right? If the right-handed limit, if the limit of f of x as x approaches c from the right is L, and the limit of f of x as x approaches c from the left is L. We just said that, right? That's essentially like saying the ants agree. Then we have our two-sided limit. So what we used to just call a limit, technically we now call a two-sided limit.
Why?
Because that implies we can approach from either side. We always said that in the past. But in the past, we didn't know about the existence of a one-sided limit, right? Now that we do, we got to be a little more specific. our normal limit of the past, and we'll still just call it a limit most of the time, but technically it's a two-sided limit, right? Whereas these are specifically one-sided limits. Okay, so how do you suppose then we could modify? I'm okay to leave this. Do I need this here for a second more? Are we good? Okay.
Wait.
Okay.
Wait, is that for
Wait, what's the one in the blue?
So that's our normal limit, right? Yeah, so our normal limit, the limit of f of x, as x approaches c equals L, like we've always done, that's only true if that and that are true. If the one-sided limits are true, right?
And those have pluses and minuses.
Yes, that's got a plus and that's got a minus. Yeah. Right? Does that make good sense to everybody, what I'm saying there with that? The limit from the right and the limit from the left have to agree on the same value for the two-sided limit to exist. Okay. All right, so let's go back a little bit then to here. So if we wanted to revise this now to say, okay, continuity on a closed interval, what am I going to have to do? That all I got to do is I've got everything accounted for except the two endpoints, right? Does that make sense? I'm not going to write this whole thing out because it's in your book, but if I say it, I think it's going to be good enough. So what we've got up here accounts for all this stuff. Now we just need to fill in the endpoints, right? So continuity on a closed interval would be true if, so how would we define, let me write this part down. How do we define continuity on the closed interval from A to B? And everybody understands the brackets mean a closed interval, including the endpoints, right? Okay. Well, continuity on the closed interval from A to B exists if continuity on the open interval from A to B exists, and what else? And we can say that the one-sided limit, the left-handed limit here, right? The limit from the right of the left endpoint meets those criteria, right? So in other words, at the endpoints, we've now got to be able to say that for the left endpoint, we have to be able to say our first criteria is that f of a exists, right? Agreed? What do you suppose the second one's going to be?
The function's defined.
Well, we just said that, f of a exists, so the function's defined at a. We got to be able to say
It's a real number.
the limit exists. The limit of f of x as x approaches a plus from the right exists. Does that seem like enough?
Nope.
No, because there's still one kind of thing that could happen that we haven't accounted for. What's that? Oops. Yeah, it has to agree. Otherwise, we could get something like this, couldn't we? Right? Because that works so far. It meets these two. The function exists and the limit exists, but they just don't agree. So then the third thing would have to be that the limit of f of x as x approaches a from the right equals f of a, right?
Well,
Agreed?
So that's like the little finger gesture.
Yeah, now we've accounted for, now we've pinned this endpoint down to right there,
Okay.
right? So if we want, once again, what are we doing here? We're adding we've already taken care of the open interval. All the points between A and B, if it's continuous there, everything else is done. We just got to pin down the endpoints now. Well, that pins down the left endpoint. How do we pin down the right endpoint?
these opposites with the negatives.
With the negatives, right? It's going to be the same deal, isn't it? We're going to be approaching B this time, right? And let's go ahead and write this. right? So if we want to do the left end point,
Right.
I mean right, sorry. Now we know, what's our first condition going to be?
F of B exists.
Second?
Limit F of X as X approaches B plus.
B
Negative.
minus exists. And then the important one that really accounts for everything. They're equal, right? They agree. Now we're done. Now we have just defined continuity on a closed interval. Okay? All right, so one other issue that we need to deal with, really a minor one, is this guy. Okay, what about discontinuities? We need to be able to distinguish between the two very different kinds, right? We've got two types of discontinuities. Removable are the kind where they're point-like, just a single point that needs to be changed, and we can repair the function, right? So technically, a discontinuity is removable if it can be removed by defining or redefining just f of c, right? So we're saying we have a discontinuity at c that can be repaired by either filling in or dragging a single point. Here would be some examples then of the two kinds of removable discontinuities. So it would be something like, here's the function at a, and there's one, that's removable, right? Agreed? All I have to do is fill in a point, okay? Or even that is removable, right? All I have to do is drag a point, just redefine the function at that one point, and I'm fine. So they're minor repairs, right? Minor repairs. All we have to do is just fix a single point, redefine the function at a single point, and we're set. Okay? Non-removable are major discontinuities, where we're going to have to move an infinite number of points to repair the function. Major overhaul, right? So what's an example of that? Yeah, break in the function, something like this. In order to repair that discontinuity, I need an entirely new function, right? I mean, if I want to drag these two ends together, that's changing the whole function. Okay. What's another example? An asymptote, yeah. Right, an asymptote is irreparable also, because obviously the function doesn't even exist there, right? But I could never repair it because the top is infinitely high. Okay. So those are removable, that's removable, these are not. I'm going to make a correlation too. I can't remember if I've said this or not, but I'm going to say it now. We'll say this a bunch. What do you think? Let's just talk about holes in the function. How do you think we get a removable discontinuity in the form of a hole? I think you've already answered this for me. But think back to your, albeit limited, but probably sufficient history with functions. Tell me, when did we get holes in the function? And this came up when we were introducing the concept of a limit. Everything. When there's, right, so when there is, it shows up, you go a little further than that. In terms of a limit, remember we had three different kinds of answers to limits, right? Which of those three types of answers, I'm in the way here, which of those three types of answers would always result in a hole in the function? Okay, remember we had three types of answers for limits. First one, indeterminate. There we go. The second one, indeterminate form, means hole in the function. Now think what that means in terms of the function. That means in terms of the function that there is somewhere there is going to be this. You know, if we work hard enough, we're always going to be able to find factors that cancel, right? And when we cancel the factors, we fill in the hole essentially, right? Okay, when do you suppose that we find asymptotes?
When you can't change one point, you can't fill it in.
Okay, but which of those three kinds of limit answer, when we try direct evaluation, which of the three do you suppose corresponds to a vertical asymptote for a function? No limit. So that's gonna happen where there's an x value that makes, so an x value is a zero of the bottom, makes the bottom equal zero, but not the top. Those will always correspond to asymptotes. So it's kind of all coming together a little bit, isn't it? Okay? All right, so how about in our remaining time here, why don't we take a look at the upcoming assignment and just kind of troll for some problems that you'd like to maybe in advance take a better look at, okay? There is. I'm gonna turn it on right now. It's 1.4. Yeah. Oh, it won't be for a while. It won't be for a while.
How many questions are there?
We can see.
10.
19.
Holy cow.
Yeah, it's a big one. Okay, so let's have a look at some of these. Hello. There we go. Okay, so on these first couple, when you see something like that's int, that says the limit of intx as x approaches 3 plus. What do you suppose intx is?
Integer.
Greatest integer function. That's another way of writing it. Okay. So just going through, I'm gonna go till I find one. Okay, how about this? Let's look at this guy and make that bigger. Can you see that?
Yeah.
Okay, the question wants to know. This is bad, isn't it? I need to make that bigger. So let me. Yeah, here. Let me grab this one. Hang on. Six minutes? Okay, that's all we need. Okay, have a look at this, please. Here we go. Okay, so there's our function. True or false? The limit of f of x as x approaches -2 from the right is 4.
Yeah, true.
No.
No. Wait, that's on the left. No,
-2 isn't even on there.
Yeah, where is it?
True.
Yes.
I'd say it's false. No, but this
And
is
it's coming, so it's going to the left.
It's false.
So true.
It's true.
Yeah, it's
true.
No.
Hunter seems very confident. Go explain.
I understand.
Yeah.
Okay, so.
Yeah, let's
obviously
let's-
going to the right, or from the right to the left,
Mhm.
so when you get to -2, you go straight up and it's closed down with 4.
Right, and we don't care that it actually is, but the limit, wouldn't you agree that the ant, pretty clear the ant anticipates stepping there, which is a y value of 4. So the answer
So
is
he's coming from the bottom?
true.
So it's coming from the opposite side.
Right.
Going towards it.
Okay, now I'm gonna tell you something here that I think is helpful. I think a lot of times when people look at this is just sort of the way our brains work, is this happens again and again. Remember that this plus or minus is purely a horizontal thing, right?
Yes.
The functions could be like, what if this function were turned up, for example? Then we would be approaching from above as we walk to the left. Now we're approaching from below. That's irrelevant though, right? All we're doing is we're just pushing the x value towards -2. So don't confuse, and this really happens a lot, don't confuse this plus sign with meaning, from above or from below. For some reason that always seems to happen. Yes, Shane?
So, let's say it was, x when it approaches -2 from the left, then would this statement be false?
Yeah, because you can't approach from the left.
Okay.
right?
You can have an ant open circle?
No, because, okay, shh, too much talking. Okay, that's a good question. The question was, what if we were approaching, what if this were a minus instead of a plus? And that's impossible because the ant has nowhere to walk to the left of -2. You can't approach from the left because the function doesn't exist to the left of -2.
So you can't come into it.
Right.
Okay.
Okay. No, it's not. It's not. But this is this was a one-sided limit, wasn't it? Because it had the plus sign there, right?
Yeah.
But are all the problems true?
But isn't there a break in the
No. Very few.
What if there was an open hole? Wait.
Okay. Okay, the question now, Janelle's question is, what if that were an open circle there? Would it change the answer?
No.
No.
Where it thinks.
Exactly, because it's a limit. So it's where he anticipates step.
Wait,
Right.
what about positive two?
Okay, hang on, here's another question.
What
Yep.
if there's positive two? Does that mean it's
Okay.
breaking a function so it goes
Let's do another one with the same picture. So you tell me, true or false, the limit of f of x as x approaches 2 from the right is 4.
false. True. There's a break.
It's like 2 seconds. It's 0.
False. It should be 0, right?
Okay.
Okay, hang on. Why? Okay, approaching from the left, right? Here's positive 2. Approaching from the left means the ant is walking up the hill towards a y value of 4. So that would have been true. Approaching from the right, like we did here, right? Approaching from the right, he's walking from the right along this flat plane, and he approaches y equals 0,
Yeah.
right? Okay, make sense?
Yes.
Okay, one more for you, and we're out of here. True or false?
True.
True.
Oh.
False? How come? Doesn't matter.
That's where he thinks he's doing stuff though.
Doesn't matter, does it? Because,
It's just wherever he thinks.
okay. So the answer is true. Yeah. We got it. Well, okay, hang on, one more question, one more question. This is a really good one. Listen, please, stop talking. Okay, the question is, would this be a two-sided limit? Yeah, it could be. It could be. We could say this. This is important, though, because you're going to run into this on the assignment. The limit of f of x as x approaches 0 is 0. But that's also true. The one-sided limit is also true, isn't it? Yeah.